Good morning. No, wait a minute, scratch that. You have no way of knowing whether it's a good morning or not. It could be midnight, it could be morning, but it could be going terribly. But I digress. Anyway, this is Professor Grenfell's continuing series on Math 12 statistics for Riverside City College, RCC. Go Tigers. Let's continue on. So this is still Chapter 10. In the first section, we're continuing on talking about the idea of correlation, linear correlation. And now what we are going to do is we're going to develop an idea that we can kind of put a number to. The correlation coefficient, as it were. And this is just, remember, a coefficient, what is that? That's just a fancy mathematics way of saying a number of some type. So that's exactly what we're going to be doing here. We're going to be trying to calculate so that we can, in numerical terms, determine whether there is linear correlation. So the population correlation coefficient is denoted by the Greek letter rho. So it kind of looks like a little lowercase p, but just, kind of more curly or whatever, and it is pronounced rho. So it's kind of like their equivalent for R, I suppose. And this is the correlation that we compute by using all possible pairs of data values. Remember, we're looking at paired data. We have one variable as X and one variable as Y, taken from the whole population. So remember, any time that we are talking about a value that we compute for a whole population, remember that that's actually impossible because we do not have all of the data for the whole population. There's no way that we can. So what is this rho? Remember, this is a hypothetical value, and we have to test this. Okay, so there's no way of actually computing the exact value of rho. We can make a hypothesis about it based on our sample computation, and then we can test that hypothesis, performing, of course, a hypothesis test, because we're experts at that by now. What we will talk about, instead of talking about the population correlation coefficient, what we will actually calculate is the linear correlation coefficient. But the key thing that we focus on is the correlation coefficient. We just call it the correlation coefficient. And in this case, what we're going to be computing every time is using the data from our sample. So what we're going to be computing for our correlation coefficient, we're going to use R, right? So this is the sample correlation coefficient. The sample correlation coefficient. So I'll denote that by CORE-COEF. The correlation coefficient, the CORE-COEF that we're going to be using is what we refer to as the PPMC. This stands for the Pearson Product Moment Correlation Coefficient. So this is basically just the way that we will do our calculation. It's named after mathematician, statistician, almost triple threat, Carl Pearson. So we'll just refer to this as PPMC for short, and this is how we are going to be calculating our correlation coefficient for our sample. The formula for the PPMC is, remember we denote that by R. Okay, so R is equal to N times the sum of the product of all of the pairs X times Y minus the sum of all of the X's times the sum of all of the Y's. And then that is all divided by the square root of, here we have a product again, n times the sum of x squared minus the sum of x, that whole thing squared, and then we do the similar sort of thing, n times the sum of y squareds minus the sum of all of the y's, and that whole thing squared. Whew, okay, yeah, that looks a little bit ridiculous. The good news is I won't make you compute this by hand 50,000 times, just 5,000. Sounds like a good deal, right? Yeah, so I'm just teasing about the 5,000. Maybe just 500. Okay, no, still teasing. We are going to do at least a couple of examples so that you are at least capable of doing them by hand if necessary, right? For of course, for small data sets. If you have to do this for large-ish value of n, of course, you're going to want to use, a computational device, a little maybe more sophisticated than just a scientific calculator. And I'll show you about that in maybe a subsequent video. But for the moment, let's do example 10-4, page 554. And so this one says, compute the linear correlation coefficient for the data in example 10-1. Okay, so we'll go back and take a peek at 10-1. Okay, so here's the data. We had data from 6 car rental companies, the number of cars in thousands, and then the revenue in billions of dollars. Or, I'm sorry, I believe that it's the number of cars in 10,000. Yeah, that's what it says here. So I've copied all of that down for us. They've, conveniently enough, they've told us the value of x and the value of y here. But the good news is from the formula, and it makes sense that it should be like this. If we got it switched around, if we had it confused in terms of which one was the x and which one was the y, the value of r would be unchanged. So what we're going to do with this table is, you notice here, I left in a little bit of blank space right here. Oh, my finger slipped there. Okay, we get a little blank column right here, and in this column, I'm going to calculate and write down the x squared value. So remember, the formula that we're looking at for the Pearson product moment correlation coefficient, the PPMC, it might remind you of that shortcut technique for computing the standard deviation when we had one sample for one variable. And essentially, we're kind of doing that same thing for both x and both y. So what we'll do over here is we'll include a little column, and we'll write down all of the y squared values here. Let's separate this, and just put a break in the graph right here. And then in this last column, another little space here, go ahead and write in the values for x times y. And so one by one, we'll just go through this whole table. In this next column, we'll look at the x column. All right, we'll look at the x value in the x column, and we'll go ahead and square that. So this first value here, we'll write in 3,969, 0. 841 in the next row, 432.64, and so on and so forth. And we'll continue and fill in the rest of this column. So continuing on, we filled in that whole column for x squared, and then we'll proceed onward to fill in the column for y squared. We're just looking at the value in the previous column and squaring it. So that first one is 49.0. Oh, silly humble brag, but no calculator on that last one. That's okay. It's silly to do, because obviously I want to put in one point here. Do this with technology. I want you to be able to write out all of this work. So, you have to construct this whole table, but don't do this by hand. When you use your calculator, go ahead and make sure that you got all of these carefully. So this next one is 15.21 and so on and so forth. 2.1 squared, we'll go ahead and do that. 4.41. So, it doesn't take too long. Just do this on your own. Make sure that you're able to write this out. But I don't mind if you use technology after that fact to go ahead and verify your answer, right? Make the computer do this to just double check. You write out your work carefully, and if there's a discrepancy, you should then be able to go back through your work and pinpoint where the badness happened. Yeah, so sorry about the rant there, but so just continuing filling in the rest of these values, and then in this last column, we're going to go ahead and look at the X column, look at the Y column, and just multiply these two values together. So 441.0 for this first one, 113.1, so we got that by doing 29.0 times 3.9. And then 20.8 times 2.1, that is, according to the calculator, is 43.68. And here's just an extra little secret. This may sound silly, but I am literally touching my fingers to these two numbers, 19.1 and 2.8. So I'm paying extra close attention to the fact that I'm multiplying 19.1 times 2.8, and I get 53.48. So that way, I'm doubly careful that I'm going to be multiplying the correct values. Okay, just a little trick like that can help you focus just that much more. And so there we just did 13.4 times 1.4, and we got 18.76. And then finally, 8.5 times 1.5, calculator says 12.75. And so then, of course, what we're going to be doing, the reason that we're doing this procedure is because, remember, we'll go back up and look at the formula in just a minute, but this formula requires all of these different values. So remember, in the formula, we're going to be using the sum of the x's. And remember, we're going to actually be squaring that or multiplying that whole thing times something else. So we have to add them all up before we do that squaring or that multiplying. Here, all of these values in this column are whatever we had for x squared. And that sum of all of those values is involved in the formula. Likewise, we've got the sum of all of the y values. That didn't look great, but oh well, doesn't have to be perfect, I guess. The sum of all of the y squared values. And then over here, these are, remember, these are x times y, so this is the sum of the x times y values. Remember, we do those multiplications, x times y, first, those are all of these, and then remember, we add them all up. Okay, so that there does take a little bit of doing, but it is very straightforward. Right, procedurally speaking, you just, the steps are pretty clear cut. You list all of the x's and then leave an extra column for all of those values. You're going to just take whatever's in that column and square it and put it in the next column. Right, then you've got your y values. You just copy all of those down. Next column after that, you've got your y squared values, and then here all of the x times y values. And add up all of those columns. And then remember, I always say attempt writing down the formula before you look it up. Okay, so there is R equals N times the sum of X times Y. So that's the first thing that we're going to put in. That 682.77 is going to go right there. Actually, I forgot that I went back up and counted. The sample size, N, is going to be in there as well. We have 6 car rental companies, so we're going to insert 6 in place of N here, here, here. Minus here the sum of X. We're going to be substituting in 153.8. The sum of the Y's is going to be replaced by 18.7. I've almost run out of colors, but then the next thing that we're going to put in is the sum of the X squared. And so remember, that we actually have to do. We have to square all of those values and add them all up. We cannot just take this one over here and square it, right? Well, we are doing that, but the point is the blue underline here and the orange underline here, these better be different values, or else we'll just have 0 in there, and that'll indicate that we did the calculation wrong if any of these parts are exactly 0. Right, what's next? Well, like I said, I almost run out of color. So the sum of Y squared there, so we're going to substitute in 80.67, and then going back to this one, the sum of Y, and then we square it, so we're going to take 18.7 and then square that value. Substitute all of that. Okay, so we do that whole computation, right? Make sure you substitute this in very carefully on your scientific calculator. And so what I read out here, the first couple of digits are 0.98197, and the rule that we are going to be using for the PPMC in terms of rounding, how should we round this? Well, we're going to round this to 3 decimal places. 3 digits past the decimal points. So that would be to the nearest thousandth. So that would round to 0.982. And just a couple of quick things about the PPMC. This is always going to be in between -1 and +1, and possibly equal to either of those values, so inclusive of the -1 and +1, those extreme values. Notice this is so very close to +1. And this essentially indicates that we have a very, very strong positive linear correlation between X and Y. The closer it is to +1, the stronger the linear correlation in a positive sense, meaning as you increase the one, the other increases as well. The closer that value is to -1, that indicates a stronger negative linear correlation. Still very, very correlated linearly, except just as you increase the X, the Y will decrease. So you have a correlation line or regression line that has a negative slope. So we'll end this there, and we'll come back and explore the notion of testing the population coefficient in a subsequent video.